Hi, hi. Our next speaker is a DevRel and an educator, electronics tinkerer, and hacker extraordinaire. He's also the man with the bow tie. So please join me in welcoming to the Hackaday Supercon stage, Shawn Hymel.
All right, thank you, Elliot. I am going to start this talk off by saying I'm about to disappoint all of you. The demo does not work. Anybody who's done demo lives knows this trouble. Yep, I see a lot of nods. I will quickly say, does anybody have a 3D printer or worked with a 3D printer? Yes! Does anybody ruined a print because they had moving air and they didn't have the 3D printer in an enclosure? Yes! That is exactly what is going on in here, and I have to say, while I am very thankful that the coordinators have upped our air systems, it is destroying my demo. The air system is too good. So I'm thankful that it's really good, but what happens is it moves air across it and it completely destroys all of the gases, and the temperature is the big thing that I'm collecting from this. So I'll go into some reasons why that might be in the presentation, but if you follow me on social media, you've probably seen this, so you kind of know what's coming, but I've made some modifications and I'll talk about those. Let's start off by talking about toasters. Everyone has probably used one of these with a basic timer. There are some great teardown videos. You can see how these work. These numbers mean absolutely nothing. Generally speaking, these are a really basic timer circuit. It might be like a 555, it might be like a 4-bit processor, or the older ones, it's a variable resistor that charges a capacitor. Once that capacitor reaches a certain charge level, it triggers the cancel mechanism and your toast pops up. But if you use these, you know how frustrating they are when you put different types of bread in, different starting temperatures, and sometimes you end up with burnt toast. So my quest was to solve that, but it's already been solved. There's this nice patent that was filed in 1933 that solved this problem. It uses a bimetallic strip that senses the surface temperature of the toast, and when that reaches a certain temperature, it pops the toaster. Now, I could not figure out why we still don't do it this way. If anybody knows, please come find me after and tell me why we don't still use either bimetallic sensors or some type of surface temperature sensor as a feedback loop to our toasters. I have no clue. There's a great video. Many of you have probably seen this by Technology Connections on YouTube. He does a teardown of this 1940s toaster that uses this technology, and he's like, this toaster is better than anything you're currently using. And he even shows you how to update it with like an actual ground connection so it doesn't burn your house down. So, we have put AI in toasters. It already exists. This is a nice $700 toaster oven that you can get from June Oven. It has a camera in the roof. It looks down over whatever it is you're toasting. It could be bread, it could be cookies, whatever it is, and uses machine learning and computer vision to figure out exactly when those things are done. It's a great invention. It also costs $700. So if you have that to spend, go for it. Please tell me how the Nest of toasters works for you. I am not buying one. I wanted to try something different. This is completely silly, but I thought it would be a lot of fun. If you remember this from a couple of years ago, Benjamin Kabe made this artificial nose using some neural networks. It takes gas sensor data from the Seed Studio multi-channel gas sensor. It's like VOCs, carbon monoxide, ethanol, something else. I have them listed in just a minute here. He combines those, he shoves those all into a neural network, and he does a simple classification model that can determine the differences between things like coffee, tea, bread. What else can he do? He says he can do different types of spirits. So mine could identify spirits versus bread, but I could not get like different types of whiskey. I couldn't replicate exactly what he was able to do with this, but you know what? It was good enough. I still want to take it to the next level and do something with it. So that's where we get to this idea of using this idea of an artificial nose to control some type of appliance. In this case, I want to control a toaster simply because it's a contained mechanism where all of the gases are coming out in one area rather than trying to put this on top of like a stovetop, and that just sounds dangerous to begin with. So I'm starting with a toaster. So here's the idea. I put some gas sensors. They sit up here above the toaster, and they're going to collect the gases as they're coming off, and I'm going to save this data. I saved it in a CSV format. I then use this data to train a machine learning model. In this case, I'm using a regression model instead of a classification model, which is what Benjamin Kabe did. I want to predict the number of seconds until the toast is burnt. So if you're familiar with something like predictive maintenance, this is the same thing. I'm trying to figure out how many seconds until something breaks, or in this case, burnt, and then trying to stop the process before that happens. I want to perform maintenance on my toast, and by maintenance, I mean eating it. So once I have that machine learning model, I'm going to put it into my microcontroller and pretend there's sensors up there because I'm still collecting sensor data. This is now I'm getting into inference where I'm taking that sensor data, I'm doing something with it, I'm trying to predict seconds until burnt, and then I'm going to control the toaster that way. So I have to hack the toaster to control that lever mechanism to pop the toast. And this is the kind of idea of what I'm going for. I'm predicting number of seconds until burnt. Where that green line is, say about 30, 40 seconds before burnt, that's where I want to pop the toast to get golden brownness. Now, I know some people like burnt toast, but for me, I wanted a little less than that. So if you're using this, if you recreate this and you like burnt toast, just set that threshold to 0 instead of 40, which is what I did. So have at it, it's still very subjective. And then of course we get to put a bunch of toast through it. So here's a close-up of what I have on stage right here. This is a bunch of different sensors. I think there's like 8 or 9 different gas sensors I have on there, plus temperature, humidity, and pressure. I just threw the whole kitchen sink at it when it comes to collecting sensor data. And then, of course, I had to burn a bunch of toast to collect that data, and I end up with something like this. Now, you can see the different, I've got temperature up there, which I think I cut off, oops, humidity, pressure, carbon dioxide, 2 different types of volatile organic compounds, nitrogen dioxide, ethanol, carbon monoxide, and we have ammonia down here. So interestingly enough, I was discussing this on Twitter, Benjamin Kabe himself reached out to me and said, hey, take a look at this research paper where they showed that ammonia actually can pick out your different, or your, where that burning happens in food. And so it was a research paper. I'm like, cool, let's just throw an ammonia sensor on there and collect the data. But interestingly enough, I don't see a spike. So red is where it was burnt, and this is very subjective. As I'm collecting data, I'm looking over, I start the process, I put the toast in, I start the process, and I actually click this button, and this is where I set a flag or set a variable that says go from ambient into now I'm toasting. And then I would just sit there and look at it. Okay, yeah, that smells about burnt. I would click the button again, and then that would mark it as burnt. So it's highly, highly subjective. So keep that in mind going into this. This is where I think the toast is burnt. And I would do this a whole bunch of times and get data that looks something like this. As you can see, there's no spikes. There's nothing here that says, okay, yeah, we're definitively burnt now. But I'm going to go ahead and throw this into a neural network to see if it can do something with this data and give me some sort of prediction. I will say it worked. So there's a video out there on DigiKey's YouTube channel where I do have this working with all of this sensor data. But this is where we get into the fun part, where we do this thing called feature selection. And feature selection is kind of like dimensionality reduction. We want to take all those dimensions, what was that, like 9 dimensions, and reduce them down. So in dimensionality reduction, we do a transformation on that data to get fewer dimensions or features going into my machine learning model. It's really slick, like principal component analysis, super cool. The issue is that a lot of times you spend more time computing the principal component analysis or whatever algorithms you're using for dimensionality reduction than you do in the neural networks if you're doing a very simple model or very simple neural network. So I don't want to do that. I want to do feature selection where we use some techniques to figure out which features do I care about in my model or the model cares about, and let's just drop all the rest. When it comes to sensors, this is super important because it means I can drop entire sensors. If I ever brought this to production, it means I could save on board space, I could save on cost, I could save on energy, and everything else, and computational complexity. Great. So there's a number of ways to do this. I focused on unsupervised, where you look at correlation between your different features. And then there's also things that are supervised where you actually take in the model that you plan to use or something close to that, and you have the model either train or you do other techniques with the model and you say, hey, model, which of these features did you care about during the training process or during inference? So I did lasso, which is least absolute shrinkage and selection operator. Don't ask me what that means, but I will show you how it works in just a second. Unsupervised, here's all the correlation that you have. What we're looking for is anything that's kind of linear like this, or maybe like an x squared or exponential, that means the data is fairly redundant. So VOC2 seems to be pretty redundant with ethanol and nitrogen dioxide. Often it means you can drop this, but it's always a good, or drop one of these three and maintain similar information in your data. Always a good idea to drop them and then train to make sure you have similar accuracy what you expect. So always be testing even during feature selection, regardless of how good the algorithm claims to be. What I ended up doing is this supervised technique. This is lasso. And so we have our loss function up here, which is probably mean squared error for our regression model. And I add an L1 at regularization term. So during optimization, the optimizer function will try to make that loss function as small as possible by manipulating the weights in your neural network. So if anybody's worked with machine learning, this is pretty familiar. Adding an L1 regularization term now says, hey, our optimizer function, we're going to try to not only make that loss function small, but also try to make the absolute value of your weights, the summation of the absolute value of your weights, as small as possible, which kind of keeps these weights down, and it helps fight overfitting. So that's usually what you use L1 regularization term. But we can do this cool trick where we have a fairly large lambda, our coefficient up there. If we make that relatively large, between like 0.1 and 1, this will have the effect of really driving some of those weights to zero that aren't used. And I show that here. So for example, let's run our training algorithm. We add an L1 regularization term with a fairly high lambda to this first layer, and the weights that are bolded coming from the feature 4 up here, those would be higher in absolute value. Remember, they could be positive, they could be negative, but they're farther away from 0. And feature 1 and feature 2, for example, those have weights that might be closer to 0. So if we look at those weights in that first layer, we can say that feature 1 and feature 2 were not really that important in the decision-making process, but features 3 and 4 were. Now we have an idea of what this model cares about going into it, and we can drop features 1 and 2 and keep features 3 and 4, and hopefully the model maintains about the same accuracy. Once again, you want to test this to make sure you are maintaining about that accuracy. And here is what I got by doing this. So here is, when I looked at all the weights feeding into that first layer from each feature, so I don't know if these are pretty small here. So I've got nitrogen dioxide, temperature, CO, blah, 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 all the way down. And I've ranked them. So I've taken all the weights coming out of those features, and then I did root mean squared so that I can take more or less the absolute value, and then I've ranked them in importance here. And what I found is that I could probably drop a lot of these, and I looked at which ones belong to my sensor boards from Seed Studio. So ammonia, despite it being very important in that paper, was not that important, and it's a very expensive sensor. So let's just drop that. We don't need that. The SGP30 ranked very low. This was equivalent CO2 and the first set of VOCs. Those were not very important either, so I dropped those. So what I end up with is temperature and humidity, which turned out to be somewhat important. I think I could probably drop humidity, but whatever, it's on the same sensor, I just kept it. And then my multi-channel gas sensor, which is 4 of these gases. Those 2 sensor boards is all I needed to maintain about the same accuracy in my regression model. So I kept those in. I trained a neural network, so I've got 80 nodes in the first layer, I've got 40 nodes in the second, and I've got my output layer, which is just 1 node. So it's a 3-layer model, 2 hidden nodes, and I got some dropout there to help with overfitting. So I'm doing a rolling window. So this is not just a point in time. It's every 10 seconds I take all of those values and I just shove those to the neural network. And then I get a new sample, I think it's like 0.5 seconds later, I drop the last sample and then send those to the neural network. So every half a second, I'm getting a new value that's trying to predict how many seconds until burnt. Great, I have this, it's trained, I throw it all into Edge Impulse because that makes porting it out to my Wio terminal to Arduino super easy. And so I've got that, good, it works. Now time to hack the toaster. So I find which nodes, I start with ground, I find my ground node, I find the LED that comes on when I push the lever, and that tells me that something's toasting. And then I also find where the button for cancel is, and then I'm able to put that into the Wio terminal. So I'm controlling all of those nodes, and I just fish these out to my Wii terminal so that I can then control it all from a microcontroller, and I use the Wii terminal because I have that really nice LCD screen, and I can display the number of seconds until burn, or predicted number of seconds until burn. Interestingly enough, I found that when it first started, those numbers are all over the place, but as it kind of gets closer to 0, they get a little more accurate. So right around 50 seconds, it becomes accurate. I mean, they're bouncing around like crazy up until that point, and when it hits about 42, and that's really not like a hitchhiker's joke, it really is about 42 seconds, it just worked out that it was like something between 40 and 45 ends up being like the perfect toast for me, and I'm like, of course it's 42, of course it had to be. So number of seconds, 42 seconds until burnt is the magical number, and that apparently solves all of your issues, and so long and thanks for all the fish. But because it's not working for me here, because of the air issues, temperature, as you saw, plays a big factor in this. It's not just gases. I'm sure there's other gases I could throw in there and throw out temperature, but it does play a big part. One of the things I didn't show earlier is that, especially that multi-channel gas sensor, I'm just taking raw voltage. I'm not doing any sort of conversion. I'm not finding ppm, and if you were at Ben's talk yesterday, you know how useless ppm is. So I'm not doing any of that. And these are fairly cheap sensors. The data sheets really don't help you when it comes to like, how do you compensate this, right? How long do you have to bake them? I think that you have to bake them for like 48 hours, and I just plug them in for 10 minutes and say good enough. But I'm just taking raw voltages from those. I'm doing some standardization to make sure that the mean is 0 and my standard deviation is like 1 for all of my data. But other than that, I'm not converting. I'm not figuring out how much exactly of a gas is in those readings. I'm just letting the neural network, deal with all of that, because who cares? So from there, I have a video of it working, but before I do that, yes, any moving air, I discovered this when I brought to another event, if somebody walks by, it would move air away and it would mess up everything. So the obvious fixes are this is for some sort of container, so like your 3D printer approach, try something other than temperature and humidity, but then it throws off all your compensation, or whatever the neural network's attempting to do to compensate for that. So there's a number of fixes, or maybe like build it into the side here, number of things you can do, and some type of enclosure would probably be the best for this. So I at least have a video of it working, and this, you can't see it here, but this is this with the reduced number of sensors. So here we go. And I don't have sound, but you can see the numbers counting down. It gets a little more accurate around the 40s.
Ooh, all right.
It pops up around 42-ish. And of course, I get the
works.
perfect toast. This works great in my house where I don't have a whole lot of moving air, and I've tried it multiple times. If I'm in a place with not a lot of moving air, it will work. So if I can get it working here, come find me, but it'll be tough with all this good moving air around here. So that's the toaster working. And then, of course, I get the question, why did I want to do this? Because I could, right? Isn't that half the reason we're doing some of these hacks, is because it's fun? There are some potential uses for this. One, I learned a lot about predictive maintenance. There are a number of ways to do predictive maintenance, and trying to predict time until failure is one good way to do it based on sensor data. Great application, right? Imagine if your car says, oh, you don't have to change your oil every 5,000 miles, and it just says, oh, we predict you have X number of miles left until you need an oil change, or X amount of time. Now you know how long you need to drive it. Cars, it's, decent, but think about large industrial equipment where they lose millions of dollars if they shut down a production line for a day. So rather than doing that, let's predict the amount of time until pieces of equipment fail. Then we know we can get a little extra time out of that and save us $1 million before we have to do any sort of maintenance on the machine. So predictive maintenance is a big thing, and I'm learning how to do that. Cool learning experience. But after I posted the original video, I get a tweet, or I get a direct message from Hans Scharler, who is the person behind ThingSpeak that's now bought by MathWorks. And he's like, hey, I liked your video. I was sitting in a meeting with a bunch of coffee roasters, and they're telling me about how these coffee roasting machines, they just pull in temperature and humidity data, and when to stop the roasting process, it's on the roaster. So I see some nods. Anybody who's dealt with that, you're just like, yeah, okay, I think it's about ready. Because it's an enclosed environment, something like this has potential use. As a toaster, it's completely useless, but these enclosed environments for brewing beer, or something like coffee roasting has potential use cases. So maybe there's some exploration there. But other than that, it was just because I could. I wanted to throw machine learning, right? It's the next level of IoT, of let's just connect anything to the internet. Let's just throw machine learning at anything, right? See what we can do. So I have all the code if you want to make your own. It's up there on GitHub. If you want to reach out to me, I'm on Twitter. I've heard that people are moving to Mastodon, so I'm going to have to do that as well. I'm also on LinkedIn and Instagram. So I think we have a couple of minutes for questions. Do I get a thumbs up? Kind of, yes, maybe one or two. Yes?
Curious if you can make two slices of toast, one after another, how that changes the results.
Yeah, it actually works. In fact, when I was at the last event where I had this working, you could toast it and then take that same piece of toast and throw it right back in, and it will actually pick it up pretty quickly, as long as it heats up fast enough and it goes, okay, it's up to temperature, I can sense that, and the gases smell like they're getting burnt, so it'll just drop pretty quickly and pop it in like 10 seconds, 20 seconds. So it cooks a little bit, but it does actually work. And yes, I trained it all on one piece, one single slice at a time, and I could throw in two, and it would work just fine. And then I threw in bagels. I never trained on bagels. Works just fine. I haven't tried waffles yet, though. That'll be that toaster strudels. Yes? Oh. Derp? That would have been amazing. I didn't even consider that.
How did you decide how many layers to use in your
WAG.
Did you experiment at all?
Yeah, it was complete WAG, and then you just tweak some of your hyperparameters. And I started with probably one layer, and then it was like, let's try 20 nodes, 20 nodes. Okay, that doesn't work. And then so it's just kind of playing from there. And I found that like 80-40 worked pretty well. And once it got to good enough, I called it good enough, right? I could probably continue to experiment, but it's a prototype, right?
How many pieces of toast did you train on?
A lot. At least like 4 loaves. I feel bad for the food waste, but I did eat a lot of it. I had a lot of bread that day. A lot of sandwiches, a lot of like jelly toast. So, as with the case of a lot of these machine learning projects, right, I do my initial training set, and then that's, right, I go through like 2 loaves of bread, and I'm like, okay, I got something kind of working, or it's not really, and that's when Ben reached out to me, and he says, oh yeah, why don't you try adding an ammonia sensor? I'm like, cool, but now that means I have to add an ammonia sensor and retrain and collect all new data, so that's half the fun. Any other questions?